ANOVA. The ANOVA has the same principles. So it's just, we're still kind of on this flow. It's the same idea, a little more twisted, a little more tweaked. You may think it's twisted. It's still how big of a difference, how big of an effect did I see, divided by how big of a difference did I expect. But so far with t-tests, we focused on kind of averages because it's one group versus a population or one group versus one group, right? There's only one, what's the difference? There's just one difference between this group and that group, right? But with ANOVA, because I can have multiple groups, it's a little more complicated. We can't look at because there can be several groups, which differences between what groups are the ones I'm talking about when I'm calculating how big of a difference did I see? Well, it depends the groups. So that doesn't work quite the same way. So instead, what we're going to end up doing, what ANOVA does, is it compares the variability within a group to the variability between the groups. Or I should maybe say it the other way around. It compares the variability between our groups to the variability within the groups. But once you kind of get that, it's exactly the same general principle. For example, I think it may help with a visual. Let's say I've got these 3 different populations. Maybe these are kids in Vermont, New Hampshire, and Maine. And we're looking at their distribution of scores on something. And you look, each state is a different color. And the scores are here's their averages, fairly close together. Not much of a difference between the averages across the states. Certainly compared to how much variability, within each state, there's a lot of variability. And between the states, there's not that much variability. The variability within each group is pretty large compared to the variability we see between the groups. So you kind of look at this and it's, am I going to bet the farm on the fact that these differences are real? That this isn't just random sampling. Am I gonna stake my fortune and reputation on saying absolutely these are absolute real differences? Probably not. At least for me, it's just that variability is too much. That within group variability is too much compared to those small differences between the groups. On the other hand, what if it looks something like this? Same variability within each group, but now the variability between the groups is huge. In fact, look at these two. The blue curve and the green curve barely overlap at all. So the variability between the groups now is much larger compared to the variability within each group. So you can hopefully kind of see, so it's kind of getting at the same thing. We're not talking standard deviation. Now we're talking variances. What's variance? Variance is variability. We're looking at how much variability there is within a group. It's kind of my yardstick to determine, is that variability between the groups big enough? So we're going to have two types of, in ANOVA, we calculate 2 different types of variance. We calculate what we're going to call the within groups variance. It's like everyone having flashbacks to this, right? There's your within group variance, and we're going to use that as our yardstick. Exactly the same way we were using standard deviation. It's just a different form of a yardstick. We're going to use that within group variance as a way of just measuring how big our between groups are. The within group variance is that inherent variation that we see due to individuals within each group. You can think of it mathematically as it's in the population, it's sigma squared, the population standard deviation, assuming the null is true. And that may seem kind of confusing because, well, we got variance here and we got variance here. How can all of that together be sigma squared? But if you think about it, this is not on the test. Actually, we don't have tests. We just have homework. And it's open book. But if you think about it, if the null is true, what does that tell us? The null is true says there's no between, we're kind of jumping ahead, but if the null is true and there's no differences between our groups, those three distributions are going to exactly overlap. In which case, the within group variance for all of them is exactly the same because they're completely overlapping. And that variance, there's no between variance at all. It's just like one big normal curve that's superimposed on itself 3 times. What's the population variance in that big normal curve? Sigma squared. So that's, with a very simple ANOVA, that's what's, and this is, we're talking kind of conceptually with a simple ANOVA, it's sigma squared. So that's, that within group variance is estimating sigma squared. It's we can use it as an estimate of what that sigma squared is. The if the variability is equal across the groups, then we can pool it. I've actually kind of jumped ahead of myself a little bit. So that's how the variance within the groups, the S squared, is that variance that we're estimating based on our sample, because it's the lowercase s, is an estimate of sigma squared. The within group doesn't tell us, that alone doesn't tell us anything. It's just a yardstick. It's not, if it's big, if it's small. In fact, you can't really tell if it's big or small. The number doesn't have meaning on its own. It's just our yardstick. But when we combine it with the between groups variance, it becomes more useful. So the between groups variance, so the yardstick is the within, the between group variance is that difference that we see, that effect that we saw. How spread out are those samples, are those averages. Now, the with between group variance reflects the same, it estimates that same sigma squared. It estimates that within groups, that within variance plus whatever group treatment effects there are. So you can think of it, the between groups reflects that same variation that we've just seen plus any group or treatment differences. So if there's no, well, let's keep going. Well, you can see kind of map in little geek ease. So the S squared between, so notice we need to distinguish. S squared is variance, right? Because S was standard deviation squared. The variance within estimates sigma squared. The variance are between variance, and this is how you'll see it written. Variance between estimates sigma squared plus any group effects. This probably is more than, did your 573 talk this level? This is, what's the, bam! What's the guy, the chef? Emerald. I should, there's a clip I need to work in here. It's like, bam, we've taken it up, we've kicking it up a notch. This is a little more subtle, but you can hopefully kind of start to see that. So anyway, so the variance between is estimating sigma squared plus our group effects. Now, kind of how that works out in the end, just like with the t-test, how big of an effect did I observe relative to how big did I expect? How big of an effect did I observe? My variance between, divided by how big of an effect did I expect? My variance within. It's exactly the same, just variances instead of differences between a mean and standard errors. Otherwise, it's functionally exactly the same. It's approximately equal to variance, sigma squared plus whatever group effects divided by sigma squared. So if there's no group effects, let's say nothing, they're like completely overlapping each other, the F will approximate 1. Now, it can go less than 1 because there's still randomness going on here. And these are two different ways of estimating sigma squared. So you can have an F less than 1. It just tells you if F is less than 1, you got nothing. You know, that's unless you have an infinite sample size with an infinite number of groups and an infinite number of people in each group. I think 610. I think I want to cut that little bit, what I just set out. Anyway, so if there's no effect, F will kind of flutter right around 1. Now, F can, as I said, F can go less than 1. Can F go less than 0? Can you have a negative F? How do we calculate F?
Oh, no.
Why?
Because you're squaring it.
They're squared values. F can never be less than 0 because it's a squared number. Variance is a squared value. So no, F can never be less than 0. On the other hand, let's say we got giant effects. Let's say our effects are really big. Then variance between is sigma squared plus some really large group effects divided by sigma squared, which gives us sigma squared plus some really big number divided by sigma squared, so F gets bigger and bigger and bigger. So the bigger and bigger and bigger F gets, we are assuming is because those group effects are bigger and bigger and bigger. Pretty cool. Make sense? That's good. If you're following, that's good. So to calculate F, F is just one variance divided by another. We just talked about the next one, so that it can't be less than 0. The variance, so kind of going backwards here, F is one variance, is the variance between divided by variance within. The variance, right, is the sum of squares divided by the degrees of freedom. And the sum of squares reflects that total variability in our outcome. So you can kind of see it's a multi-step process to get from the raw data to sums of squares to variances to F. Now, notice too, from one sample, we're calculating variance between and variances within. So part of what we need to do is take that sum of squares, which is the total variability. I remember, think back to last week, sum of squares was the total variability in our sample. You want to take that sum of squares for our outcome. And typically when we're saying sums of squares, what we're really talking about is the sum of squares for whatever our outcome is. We want to take that total variability in the outcome, our sum of squares, and now instead of just calculating one variance, the overall variance for that, we're going to split it into pieces. We're going to take the total sum of squares, the total variance, and split it into a sum of squares that's related to between group differences and the sum of squares that's related to within group differences. And then we're going to take those sums of squares and degrees of freedom to calculate our variances, to calculate an F. So this process of breaking up the sum of squares is called partitioning the variance, or partitioning your sum of squares. Oops. Let me say, partitioning your sum of squares. So we're going to partition the sum of squares to the camera. Okay? So again, remember the sum of squares is that total variability in our outcome. It's every score minus the mean squared added up. It's like just it's the total amount. To kind of see how we're going to do this, you can think of, it helps to think of every score is a combination. You can kind of break any individual score into pieces. Every individual score is, you can think of it as the mean, plus the difference between the overall population grand mean, plus the difference between the mean for my group and the grand mean, plus the difference between my score and the mean for my group. And you can think that you can kind of break it up into those pieces, and any individual score you can break up that way. So for example, let's say my score is a 90. The grand mean on some test, the grand mean is 80, mean across all the groups. The mean for my group is 95. Then we can break my score 90 up into the grand mean, which is 80, the difference between my group mean and the grand mean. My group was 95 minus 80, so that's 15, plus the difference between my score and my group mean, which is 90 minus 95, or negative 5. So yeah, you add up 80 plus 15 minus 5 gives you 90, which is my score. You kind of think, well, that's kind of silly. But you can start to see, well, we're going to see kind of how that's all related in a minute. Now, mathematically, what we just talked about, you can write down as the grand mean is just mean y, with the bar across. But because it's the grand mean, we put 2 bars because it's, the average across the groups. Plus y bar, my group mean, minus the grand mean, plus yi, my individual score, minus y bar, my group mean. So this is just a mathematical way of writing down exactly what we just said. But instead of putting in 95 and 80 and whatever, we're sticking with symbols. Grand mean plus group mean minus grand mean plus individual mean minus the group mean. And you can actually kind of see, well, this and this cancel out, and this cancel out, and we're left with my score equals my score. So no typos. Partitioning the variance, if you're really interested, I got a video I can walk you through this. But kind of the way, how we do that. So we start up here at the top, the equation we just had. Subtract the grand mean from each side, and you end up with my individual score minus the grand mean equals the group mean minus the grand mean plus the individual score minus the group mean. Let's square each side. That's all I'm doing here, squaring each side. And then I'm going to add this up across all of the i's, all the different people. So we just put a summation for each of those. Not doing anything on the left, but here, let's write this out. So this becomes the sum of, because it's squared. Yeah, because, oh, wait, here. Yeah, did I say we squared? Yeah, so we squared. So because we squared, let's write this out. This becomes the sum of my individual score, the group mean minus the grand mean squared, because it'll be this times itself, plus this times itself, the individual score minus the grand mean squared, plus this times this and this times this. So it's 2 times the sum of the group mean minus the grand mean times the individual mean minus the group mean. Now, I won't belabor you with this, but if you think about it, remember what was one of the characteristics of the mean? The sum of the deviations about the mean is always equal to 0. So the sum of these group means minus the grand mean will be 0. The sum of these individual means minus my group mean will be 0. So on average, it'll all cancel out. So this entire piece just disappears. You can kind of show this is mathematically equal to 0. And you're left with the sum of yi, my individual score minus the grand mean. What's that? That's my sum of squares, right? My score minus the overall mean squared. Added them all up, that's the sum of squares. Equals 2 different things here. One is the group mean minus the grand mean squared, the sum of those, plus the individual mean minus the group mean squared. So here, this is the total sums of squares, right? We're going to call that the total sum of squares. That's the sum of squared variation for everybody in all the groups around the total grand mean is equal to this plus this. This is, well, it's the difference between my group minus the grand mean. That's between groups, right? It's my group average minus the grand mean. That difference squared. It's variation between the groups. So that is our sum of squares between groups. Plus, and this is my individual score minus my group mean score squared. Well, that's the sum of squares within my group. So it's my sum of squares within. So that's how you can start to separate out the sum of squares. The total we can break into these two clean different pieces. The area of the sum of squares between and the sum of squares within. Far out. Let's do just a little bit more, then we will stop. So sum of squares, we'll take a break. Sum of squares within is the sum of y minus the mean group mean. Sum of squares between is the sum of the group means minus the ground mean. Both of those are squared. We need to know the degrees of freedom so that we can calculate the variances, right? Because this variance is the sum of squares divided by the degrees of freedom. So the degrees of freedom within, so we have a sum of squares within. So we need to think of what would be the degrees of freedom within. Well, when we were just looking at one group, right, our degrees of freedom was n minus 1. And it actually kind of works out the same way. Think about this. If I've got 3 groups, and I have an n for one group, minus 1, an n for the other group, minus 1, an n for the third group, minus 1, it's my total, it's n plus n plus n. It's the total n minus 1, 2, 3. The number of groups I have. So the within group degrees of freedom is n minus k. It's the n minus the k is the number of groups. So it's just n minus the number of groups. Just, kind of intuitively makes sense, just like we would think of if we were just doing any variance. The degrees of freedom between, well, in this case, I've got 3 groups, and degrees of freedom is n minus 1. My n is, in this case, my n is k. It's how many groups I got. I got 3 groups. So it's k minus 1. And it kind of makes sense if you add up the degrees of freedom within plus the degrees of freedom between, you get n minus 1 is your total degrees of freedom. So that kind of intuitively makes sense. It's nice that those two add up to the total degrees of freedom, being they're based on the total sum of squares. Okay, so I've kind of written this out to start to look pretty. Our sum of squares within, our degrees of freedom within, our variance within is just the sum of squares within divided by the degrees of freedom within. Just like any variance, it is a variance. Our variance between is the sum of squares between divided by the degrees of freedom between. We then take that to calculate our f. The f ratio is just the sum of squares between divided by the sum of squares within. As we just kind of saw this before, right? This estimates sigma, here's our variance between, estimates sigma squared plus group. Variance within estimates sigma squared. Variance between divided by variance within is our f. And that follows a distribution, what's called an f distribution, with k minus 1 and n minus k degrees of freedom. So for the f, because there's 2 variances, the degrees of freedom, there's two degrees of freedom. Not that there's a degrees of freedom equal to 2, but there's 2 values that play into the degrees of freedom. The shape doesn't just change by n minus 1, it's changing by 2 sets of numbers at the same time. So we have to keep track of both of those degrees of freedom because they're both going to influence the shape of the f distribution. Let's stop here, and then we'll wrap up this and move into chapter 1 after a break. 10 minutes?